Our next speaker would be Dr. Jean-Louis SCARTEZZINI. Επίσης δουλεύει στο Εργαστήριο Φυσικής για Ηλιακή Ενέργεια και το κτίριο το Λέζο. Και ως διευθυντής του εργαστηρίου έχει δουλέψει πάρα πολύ στη μείωση της ζήτησης ενέργειας. Χρησιμοποιεί πολύ τα φωτοβολταϊκά μέσα στο εσωτερικό των κτιρίων και η έρευνά του βρίσκεται πάνω στην αξιοποίηση της νανοτεχνολογίας σε αυτόν τον τομέα.
So thank you very much for the introduction. I'm not sure I understand everything, but I'm sure it was right. So I would like to entertain you a little bit about the zero energy building. I would like to show you and try to convince you that, and I know that some of you are already convinced, that we have to move toward zero energy buildings, and I would like to explain you the reason, and also to show you two ways we believe are necessary in order to go in this direction, nanotechnology and spreading solar technology at the level of the urban scale, which are actually the two directions that we are investigating as researchers at the Swiss Federal Institute of Technology, and more particularly in our lab. The topic or the presentation will deal with solar technology integrated within buildings, mainly, but not only photovoltaics, BIPV. I'm starting with a picture or pictures that were taken in the 90s. Actually, in the 90s, at the beginning of the 90s, we have begun to investigate the possibility of integrating solar photovoltaic technology within buildings. We have just realized that, and I will do just a bit of history for a minute, that in the 90s, actually in Switzerland, in my country, the largest power of the PV power plant we had was about 200 watts and was located in a single place in Ticino, in the south part of the country. Today, in 2013, since a year, the power we have only on the EPFL building is 2 megawatts. So that means from this time to now, we made, hopefully, a real progress. But I would like just to, as said, to come back to this historical time in the 90s where we started with by integrating solar within building. And today I think my argument, the main argument I would like also to bring to you today, is that to go a step farther from these 2 megawatts to many thousands of megawatts and gigawatts in countries and over the world, we will and we have to make solar invisible within buildings. And again, in a few minutes, I will show you and try to convince you which way you have to choose, or we have to choose or to select in order to make solar invisible. I would also make like a small piece of history, just going back in the 70s. In those times, I was just a student, not an engineer. And in the 70s, in Palo Alto, in the California states, some of you maybe know the Palo Alto Research Center, which was called in those times the Xerox Research Center. I don't know if I'm doing advertisement here at the television, but the park in those times were thinking about how computer should be in the future. In the 70s, remember, we had one main frame or main computer per institution, and this was a case for universities and as a PFL, for example. And in those times, the people of the park were thinking about the future by setting up in rooms the computer of the future. Remember that the park researcher invented what we now have on many PCs and Apple computers, not again to make advertisement, the use of icons, the use of graphical windows. This was invented in those times, in the 70s, by the thinking of these people in this research center. And in those times, what they said, what their forecast, is that computer would be invisible in 2000 and 2010 and more. And today they are. Can you imagine that, for example, in this type of iPhone, whatever the brand is, we have a Cray computer. And the Cray computer only in the 90s was a classified machine for which we had for which people from the former Easter Bloc were not allowed to even to go and use this machine. So that was definitely a classified machine, And today, in all our iPhones, smartphones, we do have Cray machines. And PC and microchips and microprocessor are everywhere in the machines, in the cars, and certainly the forecast is that we will have chips, microprocessors in the clothes, and maybe in our body. This will come in a couple of years. Solar will be invisible. This is my statement today, and we have to do so by taking different means. The first one is to use nanotechnology, and I would like to show you in some slides the way we're trying to make solar invisible on buildings, on roof and facade, and then it will be invisible because it will be spread at such a large scale within urban sites, like the antenna of televisions or antenna of the smartphone today, that we will no longer even see it. And this is something that we have in our society when products are spread all over the country. So this is my claim today, and I would like to convince you that this will be true, and it has been true for computer development. So I will go through an introduction. I will just say some word about climate change's perspective. Perspectives are not good at all for all countries of the world, and also for Switzerland. We may lose some of the ski resort industry, actually, in tourist area, and more, with many dangerous situations. I would like just to introduce the concept of energy hub, which was the urban energy retrofit strategies we try to promote, actually, with colleagues of the Swiss Federal Institute of Technology in Zurich, the ATH, and also with my colleague Carmelier and Anderson and others through the country, through different research programs. And I will also show you some example of energy plus building, not zero energy, but even energy plus building in a very, very particular case where even historical building, what we call protected building actually in our country, can be brought to energy plus. And then urban integration, solar invisible within cities through urban energy planning, not only for cold climates or heating dominated climate, but also for hot climate and cooling low dominated climate. And finally conclude all this in 40 minutes. Let's start with just a small map of Switzerland. Switzerland is a country which is known for its mountains and not only chocolates, watches and banks. And as you can see on the solar radiation map, we do have radiation. We do have solar radiation, maybe not the one you have here. The radiation we have in the southern part of the country correspond to the radiation you have in the north of the Greece, which is for sure a rather insulated area. So we do have solar radiation, as you can see here, high the Alps and a little bit less where the city are located. Again, the solar potential is there, and as said, we are beginning to dig in these resources, and hopefully we will dig more. One thing we know, at least for sure, is that, as said, climate changes will impact the country. And this is a picture I've borrowed to the Proclim Association to which I belong, which is a connection in between the IPCC and the Swiss University and Professional Association. On the left, you have a picture of the Grindelwald glacier. On the right, you have the same glacier. The first one was taken in 1878. The second one was taken in 2006. These glaciers are dying. They are melting. We know that 80% of this glacier will disappear. We even discover that they melt, they disappear quickly than expected. Certainly, ski resorts will disappear. This means danger. Actually, we also fear that there are more floods, that there are more dangerous situations in the Alps, even in some cities with the melting of the glaciers. And this is, unfortunately, what we can already see today, and what, as you know, most of the computer models for climate changes has already slightly forecasted. What we also know is, as Claude Anaroulet said, is that we will have this will be partly the benefit of the climate changes is the reduction of the heating loads. Not 30%, the figure I have from Proclim and from their report is up to 15% reduction of the building heating loads, but plus 150% in the year 2050, plus 100% in the year 2030 of the cooling loads. Again, Switzerland is gently moving closer to the climate, if not of Greece, but at least of part of the not of the south of Italy, but of the center of Italy. This is gently coming. This will mean, and this is something we cannot accept, that the electricity demand for cooling will be there, making that the overall electricity demand of the country will grow, or is expected to grow, by 3,000 gigawatt hour per year, which means about 5% of the current consumption. Yes, and now since the country decided to ban or phase out nuclear, we are trying to reduce, and we have the mandate from the federal government to reduce by 30% the electricity demand. And here we have a figure with a plus, which is actually trying to bring us in the other direction. So again, this is something we cannot accept, and we will have to deal with. So climate changes are there. I probably have shown this slide last year. This is the response of the Swiss government, a response that the federal government introduced already 10 years ago. I think Mr. Dimitri Papadaniel presented some of these figures this morning. We have the mandate to change the Swiss society from a 5,000 watts per capita society, which is the average power consumed over the year by every citizen, day and night, 24/7. We have to reduce it to 2,000 watts, and you see here what it means for the habitat, for the food here, for the infrastructure, for the mobility, the car, and the railway transportation by train. So a huge effort, factor 4 reduction of the demand in all these domains for the whole country. And this is the direction that we are aiming at, and we hopefully will be able to reach it in 2050, maybe before, maybe later. But definitely this is the target. This means also that the CO2 have to be reduced by 60 to 80%. We are currently 7 ton per capita CO2 emission per year, and we have to reduce it to 1 ton 1 ton CO2 emission per year per capita. That's mean again, this is a factor 4, even more for CO2 emission. And this is the reason why we have a rather stringent program for research and hopefully for regulation, building codes, not only for buildings, but also for cars later on. What does it mean in a concrete way? This means that for car, we have to, when I mean we, at least the Swiss citizen and hopefully the EU, we will have to deal with or to run or to use cars that should not consume more than 3 liters of oil of fuel for 100 kilometers. And actually, this kind of car are slightly coming on the market. I don't want to advertise again, I already did it, but they are electric car, they are hybrid cars sold by large brands, car brands, and they are on the market, and slightly this part of the market is growing. 3 liters per 100 kilometers. This is the only way we could cope with the 2,000 watt society. This should be for all the cars, not only one, not only two, or not only a couple of million today, but for all the cars in Switzerland and, as said, in the EU. But the technology is there or can be brought to the real world. Same thing for building. It was several times mentioned that the Minagi building, Minagi was a label, what do you call it, a label, it's a standard that was introduced in '96. There are actually 30,000 buildings of the Minagi type in the country, and Minagi, or Minagi P to be more accurate, correspond to a 3 liter of domestic fuel per square meter per year for heating. So this is the type of building we have to aim at. Minagi P to be more accurate. This again means for heating less than 30 kilowatt hour per square meter per year. So the two objectives are there. The technology mostly are there. Now we have to spread them from the technical side by reducing the cost, by making the introduction and the way we implement the technology easier. This is, as said, the way on which we work today. To be more concrete for building, we do have today this 3 liter per square heated floor area per year. We do have this kind of building, and as said, they have to be spread all over the country. This is actually, I don't want to enter too much at the figure. This is primary energy demand. It's in megajoule. We don't use BTU. I'm sorry for our US colleague. We don't use so much kilowatt hour for building megajoule. But here, this is the current Swiss average. For sure, our buildings are not better than in all the rest of the world. They have to be refurbished. They have to be improved. We have the building code. This is actually the building code, so-called SIA 380 of the year 2000. From the year 2009, we have a more stringent code, which is very close to Minergie, and this is Minergie P, or Minergie Passive Solar, or Minergie Plus, which is again the 2,000 watt target, the 3 liter per square of heated floor area per year. This is where we have to aim at for all building. There will be a problem. There will be a existing building. This kind of target is rather easy to reach today, even with reasonable extra cost. I would even say that those buildings from a real estate value have a higher value than a convention building, because people know today that the energy cost will rise, that the CO2 problem will anyway rise, so that having an energy efficient building for the 10 years, within 20 or 30 years, will be a plus. So that regarding the cost, this is no longer a real problem. But some of the buildings are historical buildings, some of the buildings are protected, some of the building could not be refurbished in a way that they will go down to 3 liter. So that the way we have to be a little bit more flexible, and I would like to introduce the concept of energy hub that should help us to be a little bit more flexible. First of all, just to remind you, but I'm sure you know what a zero or net zero energy building is. There is a full IEA task actually running on this topic, and what's an energy plus or energy positive building is. Today, we have a Swiss building code getting close to lean building. The Minergie standard, the Swiss building code, is very close to Minergie since 2009. And again, Minergie P, the 3 liter per square meter of heated floor area per year, is about there. If then, on this type of building, you introduce, this was said by the first speaker this afternoon, if you introduce renewable technology on the roof, and I will show you some example, then with these kind of buildings, and especially if you introduce the concept of energy hub, you can have a net zero balance or an energy plus balance of energy. The building or the group of building will produce more energy than they consume. And that means we will cross over this frontier, which is a frontier defining a net zero energy building. So why the concept of energy hub? This is, again, we have to deal with urban site. As I said at the beginning, to make solar invisible, we have to spread it over cities, large cities, not only the small cities we have actually in Switzerland, but very large cities like Athens. We will certainly or probably have to deal with group of building. This is a kind of group of building, and I will show an example of a Swiss city, which is Basel, which has this kind of district. Within a district or within a group of building, some of them will be certainly brand new building, and the brand new building, and the brand new building will be or will have to be energy plus building. Again, this is something we can do. Some of them will be refurbished up to the point that they will bring to be net zero energy. Other will be slightly refurbished, and at the end, other historical building will not be refurbished or could not be refurbished enough. I know that Parthenon is not consuming any energy, but imagine you cool the Parthenon or the temple there. You cannot refurbish yet by putting 1 meter of thermal insulation. This is not possible. And this is true for many historical buildings in the European city, which have this kind of advantage of having culture in the city. So all over, of cold or cold water or electricity, we will make this building autonomous or group of building autonomous, and this is the concept of energy hub. And Florenzo this morning explained that one building could not be brought, tall building could not be brought to be net zero, but if it belonged to a group of buildings where buildings are sharing or selling heat, cold, and electricity, and storing heat, coal, and electricity to bring them to the other, bring the energy hub or the group of building to be autonomous, and all over, hopefully, we will reach the 2,000 watt society program. So to break the rule and to show the exception, which is breaking the rule, this is an example of a historical building. And actually, this historical building was refurbished. I think it was refurbished in 2010. This building, which is located in Basel. Basel is a rather dense city. It's the densest city we have actually in the country. This area was a district of the 19th century where the city was moving toward chemical industry, so they had to rise up buildings, multi-story buildings with store for the workers that were working in this area. And I will show you a picture of the district. And actually, this is again the exception to the rules. This historical building, the facade on the street side is protected, was brought to a net zero and slightly energy plus building. And I will show you. First of all, I would like to convince you this is possible with energy efficiency, solar collector on the roof. In this case, they are most invisible, but we can make them more invisible. And storage in the building itself. A picture of the district. You can see it's a rather dense district, probably comparable to, I don't have the figure in mind today, we have several theses which were run on this district. And in different cities of Switzerland, Geneva and Zurich and Lausanne. But actually, this is probably as dense as Athens is regarding the narrow configuration of the streets. And you see the building are not so high. It's a 3 or 4 story above a basement type of building. The building which was refurbished was from the 1896, was refurbished in 2009. And actually, this 6-story multifamily this 6-story building was brought to a 12 multifamily dwelling by a full renovation without touching the protected side on the street. What's about the result regarding energy? Before to go to this figure, we had to run for the overall. We had to calculate the solar potential of the district. One of the questions was, can we make this overall district where the building is located? This is in Basel. As you can see here, this is toward north, and we are actually looking from the north. So the question was, can we make a district like this one autonomous by radiation on the roof and the facade, providing that the building do not use too much energy? And the answer is yes. If we bring the energy efficiency of the building to the 2,000 watt society constraints, remember Minagi P, 3 liters per square meter of heated floor area per year, then with the solar radiation on the roof, and this is actually in kilowatt hour per square meter per year, the solar radiation on the roof, we can bring the overall district to be autonomous. Maybe not each building, but as said, groups of building, district, by using this famous energy hub. On the left here, you have a figure which is pointing out, outlining the surface of the roof that can be used for PV. And actually for photovoltaics, even in the Swiss climate, we are very close to the German southern border. Half of the roof, 50%, used from a technical and an economical perspective, can be used for photovoltaic, for solar electricity production, 50%. We made the same calculation for thermal solar, for daylighting, and passive solar means, and for solar thermal, you go up to 92% of the roof, accounting for the shadow, for the orientation, for the shape of the roof, and so on. So this is a very detailed simulation that we run with ray tracing simulation by modeling the whole district. Even a church, which is a church from probably the 16th century, was modeled here. You can see it on the picture. Then we focused on the building I presented. We focused with the same type of calculation, solar radiation for house and roof, get more solar radiation. Solar thermal, you can see that for all the facade, even the facade and the roof, they could benefit from solar thermal insulation. They have definitely the potential. And this, again, is for photovoltaics. You can see that, no doubt, this perfectly south-oriented and slanted roof can be used for PV solar production and be cost-effective, and not only from the technical point of view. So these were the, and then we had to give the work, or we let the architecture office Veredem von Zürich to do the work, refurbish the building, thermal insulation. The roof had the U value of 0.15, 0.13, so that means a very thick 40 centimeter thermal insulation. The roof, and the same things for the facade. All over, after reducing the energy demand, the solar was used for domestic auto production, active solar space heating. You have here the figure, 34 square meter of solar thermal collector integrated in the roof. We can make them more invisible. How in a couple of seconds. This means that we need a heat storage to store the heat from summer to winter. We, as said before, the 10 cubic meter of water with thermal insulation was placed in the basement, on the basement, and 30 cubic meter of water was thermally insulated, was placed in the cellar. So the only rather large intervent was the water tank of 30,000 liters, which again store the solar heat from summertime to winter. If you look to the backup heating is a grid-connected pump, which is getting rather popular in Switzerland. Sweden and Switzerland are the leading country for heat pumps. And actually, in this case, by a ground-connected heat, electricity consumption is about 10,000 kilowatt hour, and you see that the thermal production of the solar heating plant on the roof is larger than this heating plant. So again, you will see the figure. This means we have a positive situation from the heat perspective. From the electricity side, this is not the case. And this is actually the problem which is remaining with embodied energy in building, is the electricity demand for plug loads, for lighting, for appliances, which still remain high. And you can see 64 square meter of building integrated PV, which are producing 9,000 kilowatt hour per year. Probably we will get the double here of 50%. Cannot cover the 20,000 kilowatt hour per year, which is the electricity demand. So from the electricity side, it's a partial solar. This is not fully convincing, and this is actually the real problem we have. Electricity remain all over the country for most of the building the real problem that we have to cope with. And as said, the government wanting to ban phasing out nuclear, we have now to reduce this electricity demand, and the target is minus 30% for the year 2030, 2035. It's a real serious target. If we look to the figures, compared to the Swiss average, which is certainly not very good, could be worse, but is definitely not optimal. This was the situation of the building before refurbishment. This is the situation of the building after the retrofit. You see that the heat demand for space heating, for domestic water, has been tremendously reduced from the original situation. Just don't forget, it's an historical building. It's a protected historical building. Electricity was slightly brought down, but not so much, as said. This is a real problem that we have to cope with, and embodied energy is still there. If we look to the energy production regarding heat, the is higher than the demand, so we have a net zero, no doubt, and slightly energy plus building over the whole year, because there is a storage, because the storage is large enough and was designed to store the heat from summer to be brought to winter. Regarding electricity, again, 1/3, this is already better than nothing. It is certainly not enough today. And again, I think in these buildings, covering the electricity demand would be or will be only possible if we play with this famous energy hub. If we building, which may be a brand new one with a larger surface that will, anyway through the grid, bring the electricity, or maybe by a local mean or a local use of electricity to this building. So again, the solution within one building for the overall problem certainly doesn't exist. We have to group them in this concept of energy hub. I would like, and again, just to remember that even without the solar energy production, it's already fitting to the 2,000 watt target, 3 liters per. north. Can we do the same thing for the south? Yes. And I think I showed this example 1 year ago here. This is an example of a building which was built in 2010 in Singapore. We work with colleagues from National University of Singapore. We work with an architect to refurbish the building. This is actually a building from the Building Construction Authority of Singapore, and they wanted to refurbish this building, which was a building from, I think, the 70s. First things we recommended with another colleague, Stefan Wittkopf. The collaboration was so good that Stefan Wittkopf joined us, and he was not nominated in a Swiss university in Lucerne. But by working with these people, with this team, you can see that shading through the trees, shading by introducing solar, also shading, thermal insulation, better glazing. The glazing were single glass before. We gently brought down the consumption of this building in a cool climate. There is no heating need actually in Singapore. It's hot and humid. We brought down the consumption to this building to a point then that's the produced by the 190 kilowatt peak solar multicrystalline installation on the roof could produce more energy than the HVAC system. This is called an HVAC system is used by the building. Here is the figure. You can see here in the year 2000 that the overall production of the PV is higher, slightly higher. Again, it's for sure a net zero energy building, but you can see it's even slightly an energy plus. The electricity production by the solar power plant on the roof is higher than the electricity demand for HVAC, for cooling the building, and lighting and appliances. Again, I should not forget to tell, this is part also of the research infrastructure of National University of Singapore, and again was driven by the BCA. So it was an example, or they wanted to have an example of a net zero or energy plus building in a hot and humid climate. So we can bring Minergie to other climate. For sure, we don't have, Claude-Alain Roulet said it very well, and Florenzus, we don't have, for sure, to duplicate, cut and paste building design from the north to the south, but the thinking, the philosophy, the overall physics can be brought, and by rational design, by knowledge design of the, we can gently bring them to a Minergie standard in hot and humid climate as in the cold climate of Switzerland. How can we make solar invisible? You're very brave and gentle because I didn't give you the answer up to now. And this is the moment where I have to give you the answer or the partial answer we have or we suggest. One way to make solar invisible is through nanotechnology to make or to offer the miners, the stakeholders, the homeowners to integrate collectors, thermal PV collectors on the roof or on the facade by having the choice of colors. And this is actually what you can see here. This is no longer there is a company which is actually under tech transfer with our lab, and this company is promoting and building and fabricating and manufacturing this color. What does it mean to be, if you have color, basically you should reduce or you should have a reduction of the energy efficiency of the collector. Yes, there is, but I will show you in a while that reduction or efficiency reduction is very low. Because instead of painting the glass or painting the absorber or painting the cells, we use filters, we use nanotechnology covering, which is known since Fresnel did his investigation in the 18th century. We can for the eyes, reducing too much the energy efficiency. So these are the type of color, from blue to green. Even terracotta type of collector can be produced. And the way it's done, it's by using nanocomposite structure on the glazing with a different technology, either technology well known for the industry or CVD technology actually, which are vacuum chamber, which are used to deposit nano structure on diffusing effect with another patented design of a very efficient diffusing surface. You can touch it with the hand. There is no dust or no grease that will be glued or this diffusive surface. If you look to the reduction of the efficiency, actually this is the relative value of the reduction. So you have to imagine if you have a 20 today, it's actually, you can get it on the market. It's one of the best companies. It's not a Chinese one actually producing it, but this 21% efficiency of black collector will be reduced to 19 at the max with a 10% relative reduction of efficiency. And again, we have figure even better than this one. For some color, the relative reduction of the efficiency relative is in between 2 and 4%. It's dependent from the color. The greenish, for example, has the lowest reduction of efficiency, the reddish a little bit more. But again, this is relative, and it means that you lose a slight percent on the thermal on the PV solar. If you have a solar collector with 40 to 60% efficiency for thermal, this is definitely not an issue regarding the advantage you have for integration facade. So you have here just to show you this is real nano. You have here a view through an electronic microscope or macroscopy. This products, aluminum oxide, silicon oxide, which has to be deposited as thin film layers. You can see the layers. There are a couple or 10 nanometer thick, and by making, this is the trick, by making high and low indexes or by depositing film, you can choose the color by choosing the type of coating, and this is something that we can do and this company can do today. So all over, we believe that now through the integration of different projects, one will be on the campus of the EPFL, one of the brand refurbished building will be refurbished at the entrance of the EPFL, will use these colored collectors. Other integration in historical village of the Lake of Geneva, we call it the Lake Léman, will be another implementation of this technology, and hopefully there will be one in a hot and humid climates in a more southern country. Unfortunately, not Greece for the moment. It's a little bit more to the south. And this is the end of my talk. I mentioned that nano would be one solution. The other one will be hopefully the urban district. And this is actually a campus we are designing. Actually, we are designing it with the inventor of Minergie, Rodier Kriesi, who promoted Minergis in '96. We are trying to convince, we don't want to promote, we don't earn any money with this promotion, there is no action about it, it's a free association, but we try to promote this Minergie standard to our hot and humid type of climate, and this is one, even close to the Mediterranean Sea. This is one example of a campus which is actually designed, for which will be used not only the solar technology, but the design of the overall campus to shade building on the external side of the building, placing the glazing to the right place, which means we have a sun which is definitely touching the horizontal surface and the east and west. So we try to avoid to have too much glazing on the facade. We use courtyard, as you can see here, which were used in the vernacular architecture in all the northwest part. Buildings and 4 classes. There will be classroom, again, it's a campus, so there will be people and young people working there, and also by promoting shading of building by grouping them and making their shape rather compact. Even the shape of the roof actually is something we suggested to optimize. I forget to tell that there will be a photovoltaic power plant. Hopefully, we are under discussion. They will integrate this colored PV collector on the roof to make them, as said, invisible at a urban scale. If we look a little bit more closer to the building, this is what you see. This is something that the people, special or solar engineering, know that there is a difference even there between December and June. And again, we can see that the horizontal surfaces, the roof, are very important, that they're the one we have also to protect for summertime and avoid too much light by having either thermal mass insulation and hopefully solar collector all over. This will reduce the penetration of solar radiation through the roof, hopefully reduce the HVAC demand. They will still remain, even if we will try to implement all the natural ventilation or all the other passive solar technique. But the goal, and this is actually what this final figure is showing, the goal is to bring the energy demand of this building down to the, even for cooling, to the Minagi 3 liter per square meter of cool floor area per year. And you can see here the figures. Actually, these are the M building. I think there are 9. You can see here what for cooling and the appliances would be with the current regulation or the current building code in this area, which is a rather rich area, but doesn't have a very stringent building code. There is a new one, actually, which is a green building code, which is reducing the demand. And if you see the last part of the figure, this is the Minagi type of consumption, less than 30 kilowatt hour per square meter, or that means 3 liter equivalent domestic oil. In this case, not to heat the building, but to cool the building down. So we can reduce the overall demand by 70%, and hopefully the proof will be there when this campus will be built, and this is hopefully something that will be reported by other colleagues in a while. But again, it's just to show you one example. We do have other where we try to gently, transfer is not the right name, but try to convince people from other climates to use this Minagi approach, which is nothing else than what Claude Roulet has suggested and presented, with some slight constraint regarding heat recovery, but I don't want to enter in this detail for the moment. It's time to conclude. I hope that I've convinced you that solar is gently getting invisible, and by the technology spreading it will be, and believe me, we do the best we can to make the solar invisible, and maybe by reporting it again within 10 years, I will be able to prove it in a better way. The things which is sure that there is a need of urban energy retrofits. We will definitely deal with this kind of objective in our country by the mandate we have from the Swiss federal government. If you don't believe this is true, maybe you should read the last IPCC special report on renewable, which is a report that the IPCC just published a couple of weeks ago, and the solar report, which is a 150 or 160 pages a large report to take or give a lot of space to solar and solar building, active and passive. And again, this is one of the way to mitigate climate changes, one of the way, not the only one. So for sure, this type of building will take a huge place in the urban energy retrofit strategies in Switzerland and abroad. There are substantial progress in building science and urban science. Today, the technology is there. We know for different climates, I show many examples from the north and the south. We know now to do net zero energy building. We know now how to do energy plus building, either based on thermal production for the north, based on electricity for the south, where you need an HVAC system. So we know how to do that. We need now to spread over, inform people, let the technical and the engineers be aware of it, and probably also reduce some cost. But this will arise. There is some R&D remaining, and probably this is good for us, this is good for the researchers. Electricity demand is still a problem in building. We know how to make them better for heat and for the space heating and the domestic hot water side, but electricity is still something on which we definitely have to work with. Technology, energy-saving technology for appliances. Embodied energy, this was presented this morning in the other room, is getting larger on the relative scale rest of the energy consumption is reduced. So we have also not to forget the embodied energy part and energy storage. Last but not least, I believe that we will make our city autonomous, we will make our city net zero energy cities only if we will have storage facility within district, for coal and for electricity. And again, this concept of energy hub is a concept on which many of us in Europe and in Switzerland would like now to concentrate our research, modeling, and as we did actually, and as we started for European side. And finally, the integration of solar has to be addressed by research, by industry, and hopefully, as said, it will definitely make solar invisible, and when solar will be invisible, we will definitely have reached our objective. Thank you very much for your attention. There is some more information on our website, and I would be happy to answer to them. Thank you.